So let's do one final example. And this is a combination, this is a combo of techniques. We're not just going to use one technique. What we're going to do is use good calculus to evaluate our limit, the techniques that we have learned. Here is the limit as x approaches infinity, is an infinite limit, of 5x plus the sine of x over x. What's the first thing we always do? Substitution theorem. 5 times huge plus the sine of huge, all divided by huge. We have a problem. First of all, this is huge plus oscillating between -1 and +1 all over huge. That's not going to lead us to any real number value, not one that just pops out to me anyway. So the substitution theorem doesn't work for me. The next thing I'm going to do is I'm going to use some algebra, because I recognize that as long as I just have one term in my denominator, that's a common denominator. It's the same denominator for every term in the numerator. So I'm going to use that to my advantage. I'm going to use that whole common denominator mess that I learned back in grade school backwards, in the opposite direction that I was taught. I also have a main limit theorem that says, you know what? Limits break up over addition and subtraction. That algebraically cleans up to 5, by the way, right? The limit as x approaches infinity of sine of x over x. The main limit theorem tells me that the limit of a constant is a constant, and the problem using the squeeze theorem that we just did on the last slide tells me that that limit is 0. So the limit of this function is 5. As the input values head toward positive infinity, the output values head toward y equal 5. This function has a horizontal asymptote that is the line y equals 5. So there's limits at infinity. We will learn another technique. It's called L'Hopital's rule. We will learn another technique that will really simplify evaluating these limits at infinity. But for now, I think we need enough algebra practice that we're going to use our algebra trick and our algebra techniques to evaluate limits for now.